So today we are going to start lecture 26, and here I'm going to discuss one more way to calculate gradient, vector or derivatives in general, and essentially we will call this as sensitivity derivatives. So the word sensitivity is sometimes used to point out that in any simulation or model, certain design variables are such that there is a higher level of sensitivity of the objective function and constraints to these design variables. And the derivatives of the objective function and the constraints with respect to these design variables give you a lot of information about what is the sensitivity of these problems to the particular design variables, and this can also help you in selecting the design variables to keep in the particular problem and the ones to discard. Now we have seen that there are various ways to calculate the gradient vector. Now we have seen that the popular method is finite differencing, that is when your objective function is coming from some computer code. Then also we saw that the AD method is there if you have access to any kind of program which performs that for you. And now in this lecture we are going to look at a very efficient way to calculate the gradients as a part of the solution process which is used in your computer program itself. And this is by analytically differentiating the problem which you have. So essentially in many situations you have explicit expressions, or you may have expressions in terms of matrices and vectors which link your objective function and constraints to the design variable. And you can essentially go into the program and differentiate these particular expressions to get new expressions to calculate the gradients. So in this particular video, I'm going to illustrate this problem for certain calculations with regard to static and dynamic FE calculations. Now, these FE methods are methods of discretization of partial differential equations of a system. So what you typically do is you create some basis functions, you discretize these equations, you get matrix vector equations, and then you solve these matrix vector equations to get the particular physical system output which you are interested in. So as a practical example, it may be vibration, it may be stresses in the system, it may be strains, it may be information from the stresses and strains which relate to the failure of the particular system in consideration. And very often you use these kind of methods in structures such as aircraft, cars, railways, buildings, space vehicles, and so on. So there are a plethora of structures. Whenever you see a real structure which is made of materials, you can understand that certain failure theories must have gone in predicting the usefulness of this structure and keeping this structure safe from failure. And in all these situations, the finite element analysis is typically used. So this is the basic theme behind calculating the gradient vector as part of a problem, and this can be applied to any different type of problem also, where you essentially solve a certain mathematical problem to get the solutions for a physical system. So it could be in magnetism, it could be in fluid dynamics, it could be in management, and so on. So we are going to consider a FE model for calculating the displacement of the structure subjected to an applied loading. So for example, you could consider a situation of an aircraft wing where there is a load on the wing when the structure is in flight, and then the structure is going to bend. So that is what is known as the displacement. So let us say we want to design this particular wing structure. So very frequently you will have a problem where you have a minimum weight as your objective function, and you may put constraints on strength and displacement. So you don't want the wing to fail. So you have certain constraints on strength, which may depend on stresses and strains in the structure. Stresses and strains can be calculated. And also you want to put certain constraints on displacement. Displacement is the level of bending of the structure. So you don't want the structure to bend too much, and you want to have some control on the bending and different motions of this particular structure. So in all these cases, there are a vast number of methods which are out there to discretize the partial differential equations. And what these methods do is that they discretize the partial differential equations, apply boundary conditions, and in the end you get a system of equations of the form kq equals f, where k is known as a stiffness matrix, q is the displacement vector, and f is the load vector. And all these three are essentially functions of your design variables for the problem. So design variables could be the dimensions of the structure, the material properties, and so on, which we are trying to optimize. Similarly, you can calculate the stresses and strains in the structure, but they would also depend on displacement. So if you are trying to calculate the derivatives of stresses and strains and any such derived property, in the end you will have to calculate displacement derivatives, which are often needed for many structural problems. So here in this equation, kq is equal to f, q is displacement. So what we want to do is to find the derivative of q with respect to xi, which is a generic design variable. So we differentiate this equation kq equals f. So we get this equation here using the chain rule. Now we rewrite this equation so that we bring dq by dxi to the left hand side, and therefore on the right hand side we get this equation with inverse of k matrix being calculated in these cases. And again, finally realizing that k inverse f is same as q, we get this particular value. So if you want to calculate the derivative of the displacement vector, you can calculate it using this equation here. So you would need the stiffness matrix, you would need the displacement, which you have calculated before using kq is equal to f, and you need the derivative of the force vector and the stiffness matrix. Now these particular derivatives can be calculated by explicit differentiation in many cases. So if you have calculated the displacement derivatives, you can use these to calculate derivatives of strain using strain displacement relations. So there are certain mathematical relations linking strain and displacement, and these can be used to calculate the derivative of strain. Similarly, derivative of stresses can then be calculated using the stress-strain relations. So again, these are all matrix vector relations, and therefore you can realize that once you have calculated the displacement derivative, you can calculate the derivatives of strains and stresses, and therefore you can calculate the derivatives of the failure criteria and so on. Now let's go back to the fact that you need to calculate these derivatives with respect to x of I, for example, for the stiffness matrix. Now the typical global stiffness matrix which we are dealing with is expressed in terms of the element stiffness matrices, and there are NE of these, and they are all summed from J is 1 to NE, and we use the partial derivative, and we use the symbol small k to point out that these are not global, these are at a local level. So again, it's a simple approximation here, or a simple formula here I should say, and the expressions for kj may be there in explicit form, in which case you can very easily differentiate this particular problem. So if you do that, you can very easily use the same formula we have derived before, and using this you can solve for the displacement derivative, because both these derivatives of k and f can be calculated by differentiating the local level matrices and then compiling these together to form the global level matrices. So this would be easy if the stiffness matrices are known in closed form, and this is often the situation when we actually derive the equations for the different elements of the stiffness matrix and write it out. But there are certain cases where the local stiffness matrices may be calculated numerically. For example, you may use numerical integration techniques to calculate these matrices. In that case, these lower level derivatives may be calculated using finite difference, and then you can calculate the dq by dxi using this particular formula here. So here you are using a combination of chain rule differentiation as well as finite differencing, but finite differencing at the local level may be relatively cheap because it involves some local functional calls rather than a call to your entire computer program. Now let us look at the dynamic problem. In the dynamic problem of a structure, you typically have to solve a problem such as given here, that is k phi equals omega square m phi, where k is a global stiffness matrix, m is the global mass matrix, phi are the eigenvectors representing the mode shape of the structure, and the omega are the natural frequencies, which are the square root of the eigenvalues. So essentially what we do in a structure is that we assemble the stiffness and mass matrix and solve this particular eigenvalue problem, and then whatever eigenvalues we obtain, we take the square root of that to yield the natural frequencies, which are very important parameters in a structure which essentially govern its dynamic behavior. So in many situations we need to know the derivatives of these frequencies, so we are going to try to find that out. Now if you are going to find that out using finite difference method, you would essentially have to solve this problem by perturbing each design variable and doing this problem, and if the size of the problem is large, that may be computationally expensive. So what we do, we differentiate this particular equation, so we get this equation here. So you can see I am differentiating each term here using the chain rule. So k, then the d phi by dxi term, then dk by dxi into phi, same thing I apply here from basic calculus. Now after doing this, we collect the terms involving phi on the left hand side and the remaining terms on the right hand side. And what we are going to try to prove is that one of these terms becomes 0. So we pre-multiply the previous equation by phi t, and then we see that the second term here will become 0. So you can check that out by looking at the eigenvalue problem, taking the transpose of both sides, and then we get this equation here. We rewrite this equation here, and we use the fact that k and m are symmetric matrices, therefore the transpose is the same as the matrix itself, and then we get the equation here, which is 0. Therefore we now have just this equation here, and you can therefore see that the derivative of the frequency can be obtained if we know the derivatives of the stiffness and the mass matrices. So that's the particular equation here, and you can now realize that if you have calculated these derivatives as part of your computer program, it is very easy to solve for the frequency derivatives. And again, as mentioned before, the derivative of the stiffness and mass matrices can be obtained by these equations, where the capital K and M are at the global level and the small k and m are at the local level, and the local level differentiation can be done explicitly if you have explicit functional representations, or they can be done using finite differencing. But this particular procedure is going to save you an enormous amount of computer time, because you do not have to perturb all the design variables and get the frequency derivatives. The frequency derivatives will be thrown out to you as part of the solution process. So we see that the gradient calculation uses the frequency and the mode shape information and therefore can be coded immediately after the frequency calculation in your program to yield the frequency derivatives. So this is the basic thinking behind these sensitivity derivatives, is that they can be coded as part of the computer program. And if you can get it from closed form expressions, this is extremely good, and these derivatives are known as sensitivity derivatives for the problem. But in certain cases, you may have to differentiate the stiffness matrix using finite differencing. Then the computer time will be slightly more, but it will still be much less than if you were to do this particular problem on the whole structural global matrices. In that case, that problem would be much more expensive. So just like I was telling before, the advantage of this method is that you do not calculate the frequencies in a huge loop and do finite differencing. And even in finite differencing, as we have mentioned before, there is room for various problems because of the selection of the step size. And you may need to use the central difference formula in some cases. So all that is mitigated by using these kind of derivatives. So these derivatives are always possible to get in optimization problems, especially if you have access to the computer code with which you are working on your problem. Now, in many situations, especially in universities, if you are a master's or PhD student, or maybe you are working in a small company, you may have a computer program for which you have considerable domain knowledge. And then you can code in these analytical derivatives as part of the computer code. But this is not possible for commercial software, and we shall see that later, that in commercial software it is better to use response surface methods and so on. But again, in many situations, people do have their own computer code, and in that case, these derivatives may be very useful. But the thing to keep in mind is that if you make any changes inside the code to the formulation part of the problem, for example, if you are calculating the frequencies, you must make appropriate changes in the calculation of the gradients also during that time, or your code will progressively start to diverge in terms of calculation of the objective function and in calculation of the objective function derivative. So this is a lacuna of this method which we have seen in the past, where we use these kind of methods, and if a particular student or engineer did this problem and then he went away and later somebody else came and there was difficulty in it, so that can have some issues with this method. So code management is something which is very important to keep these problems in check. However, if you are able to do these kind of derivatives, the advantage you are going to get in terms of computational time is huge for computationally expensive problems. So whenever you are dealing with problem where you have large systems, maybe hundreds of thousands in size, or computational fluid dynamics or heat transfer or major structural analysis problems or uncertainty quantification in optimization. For example, if you are dealing with robust design or reliability based design methods where you may need to call your function an enormous number of times to do a Monte Carlo simulation to get estimates on the statistics of the objective function and constraints, in those cases it's very useful to use sensitivity derivatives if you can. So this is a different method in terms of finite difference calculations and other method, and it's very niche, so you have to figure out whether it suits you, and if it suits you it may be useful to use it, especially if you are a graduate student and you need to get some results from a computationally expensive problem which are very important, and the quality of the derivatives is very important for you, because in these cases the derivative quality is very good because you are not really making any approximations in the problem, you are explicitly differentiating, and the computer time saved is enormous. So you will be able to handle many intractable problems using this method, especially if you are doing reliability based design optimization or robust design optimization. So that culminates this lecture 26, and I will see you in my next video, which will summarize the methods in this chapter 4 of the book. And if you are interested in some more examples and problems, you can look at the book for such information.